Thank you for introduction. And I'm Xu Shaofu from Shanghai Jiao Tong University. And I'm very glad to give this presentation to you at ACP. And here's my title of this talk. It's Artificial Intelligence Empowered Microwave Photonic Signal Processing. And first, uh, okay. First, I'll review briefly to the background of our works and uh, next generation applications such as high-speed communications or autonomous driving and Internet of Things, they have some common challenges. They will meet the broadband signals, and the scenarios will be very complicated, and the data volume are always massive. And in the mobile devices such as vehicles or mobile phones, the weight and battery are limited. So these challenges are called for some common demands for the next generation information processing technologies, such as when we want our processing devices to be large bandwidth capability, and they should be intelligent, and they cost low energy, and they can process signals with low latency. So um, how do we realize that? We think optical technologies are a good candidate, and this is the basic structure of the microwave photonic system. And the wideband electrical signal goes into this system with an electro-optic modulation. And although the bandwidth of the electrical signal is very wide, but after it is modulated onto the optical carrier, it becomes a narrow band signal. So we say that the optical systems are very easy to process this bandwidth, this wideband signals. Due to this property, we can see many applications, such as we can build reconfigurable processors, and we can build photonic radars, and which is now very developed. It is well developed, and specifically, we can build photonic ADCs. Which I will emphasize this part in this talk. Okay. Previously, and our group are dedicated to develop a high performance photonic ADCs. Before 2017, we just built photonic ADCs with discrete components. And after that, we built our first generation prototype at 2018. We can see there are 3 boxes. It is it is very high volume, and then um, in 2019, we built our second generation, and the electrical part are integrated into one box, and the optical part is integrated into another box. And then in 2020, and we recently built our third generation, and the electrical and the optical part are all integrated into one box, and the achieved performance is in advance among international institutes. Okay, and very recently, we use our prototypes to conduct an inverse synthetic aperture radar imaging experiment. And this is experiment setup, and the signal originate from the transmitter and reflected by the target. And then uh, we receive the echo signals with an photonic ADC, and this system is working at Ka band with 4 gigahertz instantaneous bandwidth, and so we can achieve a high resolution. And uh, this is an experiment of a dual corner reflector, and which shows a resolution of 3.9 centimeter by 3.75 centimeter. And we can use this high range resolution to detect a plane model, and you can see the quality is good. And uh, uh, as I mentioned, we built our prototype in a box, which is very bulky, and now we can integrate this box, the photonic part, into a photonic chip, and this is the 8-channel photonic ADC with 40 gigasamples per second and 19 gigahertz input bandwidth. And this is the 2-channel version of this chip. But although the photonic ADC is very good and it is high speed and wideband, but there are some imperfections of the system, such as this is the architecture of the system, and such as the nonlinear EVO modulation will introduce signal distortions, and the parallelization of these signals and will introduce amplitude or delay mismatches, which will also induce distortions, and some other effects will lowering the conversion accuracy. In conventional approaches, if we want to compensate these distortions, we should introduce some compensating system, which is very complicated, such as displayed here. If we want to compensate the nonlinearity that is introduced by the modulator, we should build a balanced system, and it is complicated, and so it is also hard to control very precisely, and it can only compensate the distortions one by one. We can use one approach to compensate the nonlinearity, and we use another approach to compensate the mismatch. So it is not efficient. And so, do we have any efficient and effective alternative way to compensate such imperfections? Oh, and the AI might be a good tool to do it. Recently, okay, uh, as we know, an AI can do a very high accurate face recognition tasks, and they can beat humans in gameplay, such as well-known AlphaGo, and now the AI has conquering the multiplayer games, and it can help us to solve problems that confused humans for centuries, such as the DNA, not DNA, the RNA or protein structure prediction, and we can use it to predict the disorder silicon transition. So it can be used for our microwave photonic systems. So I introduce our recent progress on this topic, and this is the basic structure of AI-powered microwave photonic signal processing. The wideband signal is firstly enters the photonic processing system, because the photonic processing system is broadband and with high tunability and high speed, and it converted to digital data and enters the digital data processor, and which was deployed with a deep neural network. The deep neural network here can do many tasks. It can do distortion and elimination, or it can do some recognition, and it can do some function recognition or regression. So it can output the refined signal, or it can output some decision making results. So, but we should train the neural network to function as a good one. So we should use some training equipment. So this is a very basic structure. However, we cannot use a conventional AI training procedure to do this task, because I will introduce the conventional AI training procedures. And normally, we use a very good tool to acquire the environmental data into a very good form. This is called ground truth acquisition. We use a very good device. And then we use the good data to simulate the inferior data. And then we use a good data, inferior data to train the DNN, and the DNN can do a prediction from the inferior data. This is the conventional AI training. But in our microwave photonic system, the good device is somehow not available in many cases. So, and we cannot use this training procedure. We use this. We generate the data and use an inferior system or an inferior device to acquire the inferior data. And because the good data is generated, so we know what good data is. So we use this to train the deep neural network, so it can function as the conventional trained one. So so that's the training procedure of the AI-powered microphotonic system. So from this, we do two tasks. The first one is we refine the signals. As I mentioned, the analog to digital converter has some imperfections. So the R, wideband RF signal input to the wideband high-speed photonic sampling system, and then we use a high accuracy electronic quantizers to convert the analog signal to digital signal. And then because it has imperfections, so the signal is distorted and low quality. So we use a deep neural network to compensate such imperfections. We use a linearization net to compensate the non-linear effect, and we use a matching net to compensate the channel mismatches. That's the basic concept. And here are some results. This is loss curves during training, and the loss curve decreases consistently, so it infers a successful training. And the non-linearity recovery is successful because if we have non-linearity, the harmonic distortions is very obvious, and after the network, it is eliminated, and the signal is recovered, and the mismatch is also recovered very effectively. This is the mismatch distortion. It is symmetric to the original signal, and it is now eliminated by the neural network. And the neural network is also applicable to the complicated signals, such as a linearly frequency modulated signal. It is also effective. And overall, it can improve the effective number of bits, the conversion accuracy of the photonic ADC. Because the photonic ADC is not compensated by any conventional approach, so it is very it performs a low ENOB if we do not use our neural network, and if you use our neural network, it is improved very significantly. So and such performance approaches the noise limit, which is a physical limit we cannot break. So we can see the neuron has performs very good. And as we demonstrated that the neural network can improve the performance of photonic ADC, if we use the photonic ADC into a radar application, we can increase the performance of radar. Okay, so this is our experimental result to demonstrate the radar application. The signal transmitted and reflected and received by an untuned PADC, and this is a because it is untuned, so the performance is not good. So the signal is low fidelity. But with a neural network, here we call it MUNet. It's a new network, especially for this application. So after this network, it is now becomes high fidelity. And this is how we train the neural network, because we have to train the neural network before it can function as a good one. We, we train the neural network by generating random signals, because we want to use the generated randomness to cover the unknown randomness. If we generate enough random signal to train the neural network, it is possible to cover the unknown signals, which is in use. Okay. So we train our neural network like this, and this is the training result. We can say the training is successful, and before the neural network, the signal is distorted. Obviously, you can see the blue curves. It is distorted, and after the neural network, it is recovered to a high quality. And here is the STFT, short time Fourier transform of the signal. Before the neural net recovery, the spectra is very messy with many distortions, and after and the distortions are effectively eliminated. And this is a range profile after the pulse compression operation. We can see the ground truth is a green curve, and the network output is always matched with the ground truth. So we can see the effectiveness of the neural network. We compared the SFDR before and after the neural network signal recovery, and it's about 20 dB improvement. But the it is very good one because it is from the untuned photonic ADC. That ADC is not compensated by any approaches. It is only compensated by our neural network. So the 20 dB it seems very large. It seems astonishing. It shows the effect and the neural network is effective, and we conduct the radar detection using different targets such as